Hello and welcome back to the CCENT journey with me, Ryan. In this next section, we're going to talk about the network topologies and application behavior. For those who don't know, you can contact me here on YouTube, on LinkedIn, or Twitter. So what I've gone ahead and done is drawn some topologies. I've drawn two. There's a campus design down the bottom here, and there's a service provider network or an ISP design for a WAN at the top here. Now, a topology is essentially a diagram that allows you and another engineer to actually articulate what we've put together and in turn help them either with the growth of the network, troubleshooting of the network, or just actually understanding how the network works the way it does. Now, a topology itself comes in two forms. It can be one, physical, or it can be two, logical. Now, the way to think of this would be physical is how the cables actually connect together. Okay, so how it connects. And logical is, the way I think of this, is from the end user's point. So if we look at this diagram down here, for example, let's say this particular router had a switch connected off the back of it, and off that there's another switch, and off the back of this switch there's a PC, and over here there's a PC directly plugged into this device. And then let's also think that this device here is completely geographically separated. Now, physically we can see that this PC itself plugs into a switch, which goes into another switch, which then goes upstream into a router, which goes across maybe a bunch of telephone poles because we're using some sort of describer line technology, into our provider network where it traverses multiple devices, eventually finds the correct exit, and again, maybe this is a DSL subscriber line and it goes across a bunch of telephone poles, gets into this router, and then off it goes to the destination. Now, from the logical point of view of the end user, it thinks that this device here is directly connected to this cloud, and this cloud is directly connected to this device. So it's kind of one hop and it's reached its destination. But physically, as you can see, it plugs into all these devices to actually reach the actual destination it's trying to get to. So another example of this would be, let's think about our home connection. We have a PC, and our PC connects to our home router, and our home router then has a link into the internet, right? From the PC's perspective, or at least from the NIC card perspective, anything it wants to know about, whether that's Google, BBC, Netflix, it sends it all to this router, and this router sends it all to the internet. So logically, this is what it looks like, right? But physically, what's actually happening here is not only do you have maybe your telephone poles or underground cabling, but also when it hits the service provider network and the internet, it goes across multiple hops, maybe even through different countries, to reach the destination, to then pass the traffic all the way back. So it's really important to know that actually when you look at a topology, you need to understand whether it's the physical or logical topology, and more importantly, when you look at topology, you need to make sure that you have the correct documentation with that topology. There's nothing worse than actually having a topology diagram that looks pretty, but there's no documentation to support it. Because you can draw pretty pictures like this, for example, but this picture doesn't tell me anything about the spanning tree protocol, or what VLANs are allowed or not allowed, or whether this whole switching network is running something called BTP, where does the layer 2 and layer 3 termination points are, nothing. So it's very important, and it's more so important that you have your topology, but you have the correct documentation to support it. What you also may come across is the type of actual lines themselves. So here we have a straight line. A straight line normally represents a Ethernet connection, whereas a lightning bolt tends to represent a serial connection. However, sometimes these serial connections, or these lightning bolts, are actually drawn to represent a WAN connection. So again, unless you know the actual documentation that goes with the topology, there'd be no way you as an engineer to be able to interpret that information. I mean, sure, you can look at this device, look at this design and go, oh, these are all a bunch of routers. We know that just by looking at it. We also know that this is a firewall, and we know that these are switches, more powerful switches than these switches, and we also know that there's some routers. But what we don't know is how that configuration looks, the speed of these cables and the state of these cables. So it's important that we have that documentation as well as the diagram, both logical and physical. So here we have the three main sort of topologies that people like to talk about and you get questions about within your Cisco certification. And by looking at them, you can hopefully put star, bus and ring against the ones that you can easily identify. So this being a ring, this being a star, and this being a bus. What I want to do is first talk about the bus. Now, bus is a older sort of topology, and it was used in the 10 base 2 and 10 base 5. Now, this was originally mentioned with a type of Ethernet where it would have a coaxial cable, a very thick cable through the middle, and then each device would just clamp on using vampire taps onto the single cable itself. If there was a break in the cable, it would disrupt the communication, and essentially everyone would send their information onto the wire, and that information would be broadcasted out every single port until it reached its recipient. And then to prevent any collisions, or to help prevent collisions, CCNA CD, which we'll get into when we get into our Ethernet section, helped prevent that. This was a bus topology. Now, physically and logically, this is a bus. If we actually replaced this coax cable with a device, let's say a hub, for example, and we had all of our PCs connected off the back of it, each of these PCs would logically be connected as a bus still, but physically connected as a star. Now the reason for that is the hub itself works at layer 1 in the Open System Interconnect model, the OSI model. And essentially a hub is like a repeater, or it's also called a repeater to be fair. When traffic comes into the hub, it's actually repeated out of every single port. So there is no difference in a hub versus this long coax cable. So a way to determine, or way to actually see the difference between a physical and logical would be to understand that this is physically a star, but logically a bus, the same as the one above. If we were to replace this hub with a switch, or maybe we replace the hub with a router itself, then we would break up this bus and actually make it a logical and physical star. And the reason for that is because a switch works at layer 2 at the OSI and a router works at layer 3. And they handle traffic differently. They don't essentially repeat the traffic out of every interface. They actually learn and to gather the information on the interfaces and switch and route that traffic where it needs to go. And when later on when we get into understanding the OSI model and these devices in more detail, this will become more clear to you. For now, just understand that logically and physically, diagrams can become different things. Moving on, we've got this one in the middle. This is called a ring topology. And there used to be an old technology called token ring. And essentially the way this would work would, a PC would want to communicate with another PC, and they would put a packet on the wire. This packet would travel around until it reached the destination PC. The destination PC will open the packet and take out the information it requires and put in the information to advise that it's being received and send it back around this ring. Whoever had this token could communicate and receive the information, and if they didn't have a token, then they couldn't communicate. Now because of that, there is no need for this CCNA CD, because there is no possible collision method, because only one person could talk at a time. This one over here and this one, this bus topology, did need a mechanism on the Ethernet called CCNA CD to actually prevent those collisions. Now, going back to what I said about the hub and it repeats the traffic, and a switch and router doesn't, we still use CCNA CD on these links, on these Ethernet links, regardless of the central device it connects into. This is CCNA CD is not something you can turn off. It's on by default, and the reason for that is because of it depends on the duplex settings, whether CCNA CD is needed, and other factors. So we'll come into that a little bit later. But for now, understand that on a bus topology, CCNA CD was required to help with collision detection and essentially to stop devices from sending frames onto the wire to then be collided with one another. Whereas this old tokening technology, which was not Ethernet, didn't require that. Moving on to Star. Now, Star is most likely something you see in your house today. If you ever think about all your equipment most likely connects into your router, or maybe you have a switch, or most likely your router itself has a built-in switch to allow multiple devices to actually connect into it. Now, the benefit clearly of a Star topology is if a link were to die, connection would still continue, whereas if a link were to die here, it wouldn't continue, because that signal that comes out onto the wire would need to be broadcasted everywhere. The downside of this would be a centralized problem, meaning if the device in the middle, maybe your router, was to die, then all devices were to die on the network. So that's something to put in consideration as well. What we're going to do is, as we go along in this program, we're actually going to get into more depth around the collision domains, broadcast domains, and CCNA CD, and how it helps us on a bus topology prevent collisions and how it actually works in more detail. For now, I just want to actually focus more on the topology side and give you an understanding of what a topology is and how it can be separate both physically and logically. Okay, in the next section I want to talk about full mesh, partial mesh, hub and spokes, and point-to-point. So let's start with what's called a hub and spoke. A hub and spoke is essentially where you have a site, normally the HQ, and it's called a hub. And off the back of this, you have a bunch of other sites, and these are referred to as the spokes. Now, the downside with this design is essentially every spoke, if it wishes to communicate with another device, it obviously has to go through the hub itself. So traffic patterns is very much like this. If the hub were to die, then no spokes will be able to communicate with each other. So it's a very critical design. Now, the reason this design is favoured is essentially because of cost. It's much cheaper to have a HQ with multiple spokes than it is to have every spoke connected to one another, especially when maybe these spokes do not communicate with each other often. It also depends on the company's desires and control that they have. So, for example, I have seen companies where they would invest in actually doubling up the resiliency at their HQ site, because maybe this is where they have their internet breakout and they want all spokes to communicate with the HQ so they can filter it through their firewalls or through their web filtering before it goes out to the internet. Now, the other design, I want to grow on this a little bit, is called a partial mesh. So let's say, again, we have a hub and spoke, right? We have our 3 sites, but this time we have two spokes themselves that maybe talk to each other quite a lot, so we put a link between them. And then maybe we have this site also communicates with this site quite often, so we put a link between them. Now what starts to happen is we have some sort of mesh going on, where some sites have some resiliency to each other and some sites do not. So it's kind of like a partial mesh. Now, obviously the benefit with this would be extra resilience. So let's say this site over here was our data center and everything was hosted in our data center, and these 2 sites had lots of traffic that would go into the data center, and rather than pushing it up to the hub and back down, we want it to actually have direct links into that data center. So this would be a way that we can utilize a partial mesh design to take load off the hub into a partial mesh. Let's say as the company grew, actually it turned out that our service provider's given us a good deal and we were able to now get links to every other site. In order to do that and to become a full mesh, then we would need to look about making sure that every site has a link to every other site. And then it becomes a full mesh design. Now obviously the full mesh design is the most desirable design, however it does add complexity around routing and failover scenarios, and also it adds the additional cost where maybe two sites or a couple of sites don't communicate enough to warrant the cost of an extra link. Therefore it may not always be wise to go for a full mesh design. Last but not least is point-to-point. Point-to-point is pretty straightforward. We have a link, two routers on the end of it. That's considered a point-to-point. You may also hear something called point-to-multipoint, which is where we have one link and it connects into another device, very similar to hub and spoke, and it has multiple points coming off a single point. The terminology of hub and spoke and point-to-multipoint I've seen sometimes be interchangeable. Some people may refer to their network as a hub and spoke, some people may refer to it as a point-to-multipoint. From my perspective, I tend to use the hub and spoke to describe a topology physically and from a service provider element, and I use the point-to-multipoint to describe how it would actually logically work from a routing protocol perspective. In the last section, I want to pick up application behaviors, and there are two to discuss. There's client and server and peer-to-peer. Now, client and server is essentially, we have a server, maybe that server sits somewhere on the internet, and off the back of this server we have multiple streams of data going to individual PCs. Now, this type of setup, the benefit of it essentially is every client has its own TCP stream, or maybe it sends its own UDP segments upstream into the central server, and the clients talk to the server and pull down its own information at its own rate, depending on many factors, including the line speed, the performance of the both host and the server, amongst other things. Now, the advantages of this sort of design is essentially performance. Depending on the server, the client and the link, there is some sort of degree of actual dedicated performance there. The other advantage is the administration. We have full control over how fast or who can download our content because it's on a central device that we tend to manage. And now the disadvantages of this type of communication is it costs a lot. We need to make sure that our server itself can handle the load that each client is essentially putting on it, and it's very complex. The complexity itself in this sort of design is far more complex to upscale the multiple servers that is required to actually handle the increased workload. The second is the peer-to-peer. And we can imagine that we have multiple PCs spread out, and they have essentially links to one another. And in this scenario, we don't have a client or server. In fact, every device is a client and server. So let's say, for example, this particular PC over here downloaded a part of a particular file that another PC requires, then he can send it to this PC upstream, and this PC will then be able to send it downstream. So essentially, every PC downloads the application from each other, not from a centralized source. Now, the benefits of this is it's very easy to set up, and the other benefit is essentially it's very cheap. There's no complex central device or to actually upscale as the increased load, as the load increases, and the more PCs that actually have the file, the faster the file becomes available for other PCs, because that bandwidth and that resource becomes available. So with peer-to-peer traffic, you'll see if one PC has it, they upload it to the second PC will then be able to upload it to the third PC with the help of the first PC, and then when the fourth one needs the file, all three will essentially have it. Now the disadvantage of this kind of design is it's not secure. You have no control over the endpoints, because these endpoints could essentially be other PCs. Some of these may have malicious intent, and essentially you have no control over the performance. So if this particular person here decides to slow down their speeds, then it will affect maybe this PC that's downloading a particular file from it. Or let's say if all three of these PCs now have the file and all of them decides to shut down, then the fourth PC is left without that file. Okay, so wrapping up the lesson, what have we learned today? We now understand what a topology is. It's essentially a pretty picture that allows us as engineers to identify how the network is logically and physically connected together, and hopefully there's some sort of detailed documentation that goes with that to help us identify in more depth what's happening with the configuration itself and how it achieves the goal that it's set out to do. We then touch base on the physical and logical topologies and why having diagrams for each one is important, and what is a physical versus logical. We said physical topology is how it actually connects to one another, and logical topology is how the end user perceives the network. We then jumped into the classic types of topologies with ring, star and bus, and then we had a discussion, very brief discussion about CCNA, CD, and I mentioned that more information about this will be coming when we get into the Ethernet segment within layer 2. We then went into full mesh, partial mesh. We then looked at hub and spokes and point-to-multipoints, and then finished off with application service with peer-to-peer and client and server. Lastly, I hope this has been informative. I'd like to thank you for viewing, and if it has been, please do like and subscribe.